So the first thing to note is an error that I made on Monday that no one pointed out until after class, so I'm going to point it out now. So the big takeaway of this exercise that we did last time was you can figure out whether our trig functions are positive or negative by just figuring out what quadrant the negative is. In this case, we got 2 pi over 3 to be in quadrant 2. In quadrant 2, cosine is negative because it's the x-coordinate. Sine is positive because it's the y-coordinate. Tangent is negative because it's the slope. Cotangent is the reciprocal of tangent, so it should have the same positivity or negativity. Right? Dividing by a negative is negative. Secant is 1 over the x value. X value is negative, so that should be negative. That was written down wrong last time. Cosecant is 1 over the y value, so that'll be 1 over a positive, is positive. You know. How many people noticed that mistake like in class when it happened? It didn't stop me? Nice. All right. So here's what I'm going to do today. So right now let's think about what the definitions we have for the trig functions are. The instructions for trig functions, well, you know what, I'm being recorded here, so let's do it here, is you draw a little unit circle. You start at the point 1, 0. You rotate forward by some angle. You land at some x, y coordinate. X is equal to the cosine of this angle. The y value is the sine of this angle. The slope, so y over x, is equal to the tangent of this angle. And then secant, cosecant, cotangent, whatever. Well, trigonometry is called trigonometry because it tells you something about triangles. So let's start building that a little bit. So let's do some right triangle trigonometry. So here's the way I'll do it. So let's see. So I'm saying that this circle is a circle of radius 1. So consider the following right triangle and unit circle. So there's a right triangle inside of a unit circle. So it's inside of a circle of radius 1. By looking at this triangle, what's the length of that y value? What's the length of that vertical side? Well, it's whatever the y value of that point on top of it is, right? So if this point up here is xy, then that opposite edge is the same as the y value. But what trig function gives you that y value? By the exact same logic, what is the length of that side adjacent to theta? Cosine. Cosine. That adjacent side length has length x. Well, that's the cosine of theta. But as a quick observation, that was built on the assumption that the hypotenuse is length 1. So when you have a right triangle with hypotenuse length 1, trig functions give you the adjacent and opposite sides of that triangle. So that's something. Let's see what happens when we just scale everything up by some factor. So I'm going to take that exact same triangle, and I'm going to multiply all of the side lengths by a factor of h. So I'll have some new triangle there. Feel good right now? Nice. So, old hypotenuse was length 1, new hypotenuse is length h because I multiplied all the side lengths by h. What is the length of the side opposite theta?
Sine squared plus cosine squared equals hypotenuse.
That'll be a relevant equation soon. So let's see what it was before. Before I multiplied all the side lengths by h, sine of theta was the opposite side. So after I multiply all the side lengths by h, what's the length of that opposite side? It's just h multiplied by what it used to be. by the same logic, the adjacent side length used to just be cosine. After you multiply all the side lengths by h, what's the length of the adjacent side? H times cosine theta. And here's the whole thing that I'm building. So if h times sine of theta is equal to the opposite side length, if you take that and solve it for sine of theta, what do you get?
Over hypotenuse.
Yeah. Similarly, cosine of theta is adjacent over hypotenuse. And I don't know, like, those two equations are at the heart of what's called right triangle trigonometry. So forget about all of that justification we just did. Whenever you see a right triangle and you know an angle in that right triangle, then the sine of that angle gives you the opposite side length divided by the length of the hypotenuse. Cosine of theta gives you adjacent over hypotenuse. What does tangent give you? Sine over cosine. Yeah, so let's use that. So tangent of theta is sine over cosine. So that'll be like opposite over hypotenuse divided by adjacent over hypotenuse. Ooh, anything cancel there? Does that simplify?
It's just opposite over adjacent.
Just opposite over adjacent. All right, so those three equations, sine of theta is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Those three equations are at the heart of what right triangle trigonometry says. They tell you that the trig functions give you ratios of side lengths. And I don't know, like, let's just list them. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And in terms of just like a short-term mnemonic, because by the end of this class, you should have those three facts bonded into your brain because you'll use them nonstop. But if you want a short-term mnemonic, if you can remember the three-syllable SOHCAHTOA, then you'll remember it all. Sine is opposite over hypotenuse, so. Cosine is adjacent over hypotenuse, ka. Tangent is opposite over adjacent, toa. And there are a handful of other like limericky mnemonics you can use to remember this, but you know, if you can remember SOHCAHTOA, you can remember. Folks feeling good? All right. These facts, that's what one usually means when one talks about right triangle trigonometry. And let's use those facts to now say something. There's a right triangle. It's got a side length of 3, a side length of 4, and an angle of theta. Let's try to use right triangle trigonometry to figure out all the trig functions at that angle. All right, so let's do it. Does one of the trig functions, do you already know one of the trig functions based on this picture? Yeah, that's a relevant fact, but not an answer to the question. Let's use that. So, what's the hypotenuse to this triangle then? 5. And on the one hand, if you just remember the fact that 3, 4, 5 is a Pythagorean triple, then you know that 3 squared plus 4 squared is 5 squared. But let's imagine we didn't know that and do it algebraically instead. So the hypotenuse of a right triangle by the Pythagorean theorem, h squared is equal to 3 squared plus 4 squared. So h squared equals 25. If the hypotenuse squared is length 25, then what's the hypotenuse length? 5. Exactly what you just said. So this hypotenuse has length 5. All right. And now let's use SOHCAHTOA to do this. Cosine is adjacent over hypotenuse. What's the length of the side adjacent to theta? What's the length of the hypotenuse? Cool. Cosine of this angle is 3/5. How about sine of this angle?
4/5. Because that was it over backwards.
Nice. People agree? How about tangent?
4/5. Or 4/3.
Nice. Cool. So if you know some side lengths in a triangle, then you know some things about a bunch of the angles in the triangle. In this case, you know that cosine of theta is 3/5. And this also goes the other way. Let's suppose that instead I knew that angle. Maybe I knew that angle was like 25 degrees, and I knew that that side length was 7. I could figure out the base side length using tangent. I could figure out the hypotenuse using sine. So I could know everything about that triangle. And I think instead of doing an example in the abstract, let's do an example which is going to be extremely applied. I'm going to measure an actual side length. So let's go to the next page. Here is the game we are about to play. So, the tool I'm going to use for this is an Abney level. Let me show you vaguely what it has. So it's got a rotating thing that will read off an angle in degrees. As with most applied things, I'm going to walk in degrees. It's also got, through this viewing hole, you can't see it through there, a little mirror so that you can see a leveling bubble at the top of this rotating thing. It's called an Abney level. So here's what I'm going to use it to do. I'm going to use it to measure some angles, because that's all it can do. And I'm going to use those angle measurements to determine the height of the back of the wall. And maybe before I even do that, I'll pass that around so people want to look at it. Click through the eye hole, there'll be something you can see if you turn the knob. And let's try to make some of the preliminary measurements. So I am going to first measure my eye level because that's where I'm going to start this from. In order to measure my eye level, well, let's just see. My eye level appears to be at 70 inches. I'm going to stand at the front of the classroom with that Abney level, and I'm going to measure 2 angles. I am going to look down from the front of the classroom to that bottom corner of the classroom. I'm going to figure out what angle that is. I am then going to look up to the back top corner of the classroom from the same standing location. There. And I'll read off what angles those are. Well, at that point, I'll have that this length is 70 inches. If I were to go straight across the horizontal, this side length would also be 70 inches. So let's just see. In that diagram, once I actually measure these angles, is there going to be a right triangle whose angle I know and where I know at least one side length? Yeah, which triangle? So I'll be able to use this triangle to find anything I want about that triangle. I think that horizontal will be something that I should try to find. Once I know that horizontal side length, I want to determine the height of that back wall. Is there enough there that I'll be able to figure that out? Yeah, what strategy will I follow? Let's see, in the big triangle, so there's the thing I'll try to get first. That big triangle, will I know at least one side length in that big triangle? And I'll know that angle? So which trig function looks useful? I would like to know the opposite, and I'll know the adjacent. That looks like tangent will be useful. So tangent's what I'll wind up using. So, cool. At this point, we have a plan of attack. And like, the starting point that I still need to hit is like making the measurements. So, I think now we're stalled long enough. I'm gonna go take the do that back. If anyone didn't get a chance, they want to like take a look at it and see how it looks. Yeah. It'll be at the front of the room. Oh, by the way, as a sales pitch, there is an extra credit that is just this example, but you're going to be measuring a building instead of the back of the room. So, let's do it. So starting from the side level, I'm going to stand here. I'm going to look at the look at the bottom of the classroom, and that bubble is now level. That is an angle of 10 degrees. I'll ask someone else to write it down so I don't have to move, because if I move then things won't be measured from the same point. So 10 degrees down. And then looking up to the back corner of the classroom. That appears to be an angle of 12 degrees up. So, measuring those, that downward angle was 10 degrees. This upward angle is 12 degrees. All right, so I said I'd find that pink side length first, so let's give it a name. Let's call that x. And it looks like this 10-degree angle has something to do with x, so let's use that. I know the opposite side length from that 10 degrees. I would like to know the adjacent side length, so I think tangent is the important thing to work with. So let's use that. So, tangent of 10 degrees is equal to opposite. Well, let's write that then. Opposite over adjacent. That is 70 inches divided by that unknown side length x. That like I could solve it for x? Yeah, I guess it'd be clear the denominator is to multiply x to the other side, divide that tangent of 10 degrees to the other side. Just because I already see people taking out calculators, what is that about?
It's like 0.0025.
I find that unbelievable. Oh, just tangent of 10 degrees is that.
I got 107.96.
I also find that unbelievable, because that's supposed to be the link to the back of the classroom, right?
I got 396.98.
I think you're an Oedian bird. So, I'm going to wait till I hear two consecutive, consistent answers, and then I'm going to write that down.
Yeah, I got 396.
Cool. I only hold the first two digits.
396.98.
I'm going to round off to the nearest inch because I don't think I have that much confidence. My hand was a little bit shaky when I measured those degrees, and like you saw how I was measuring the height of my eye line. Did you believe that I was doing that right? So I think that rounding that to the nearest inch is probably even ambitious. I don't think I even have that to that accuracy. But here's the good news. I'm not going to use that approximation anyway in the next step. I'm going to use that exact value to avoid propagating rounding errors. So let's use that. So now that I know the side length x, I guess I should call that side length y. What trig function should I use to try to find the side length y? Let's use tangent again. So let's write down an equation involving tangent. Tangent of what?
12.
Yeah, that angle was 12 degrees. is equal to what? I'll use the exact value, so I just have a name for that side element, I'm just calling it x. That look like you could solve that for y? Yeah, just, I guess like multiply x to the other side. And now I'll use this exact value. Equals tangent 12 degrees times x, which is 70 inches, divided by tangent 10 degrees. And now, in order to avoid this propagating around here, I now have a formula for the side length y. Anything suspect there? And so all of that is equal to x. So let's use that. Come on. All right, so let's see what I had. Tangent of 12 degrees times 70, I'll just remember that it's in inches, divided by tangent of 10 degrees. I'm getting that to be about 84 inches. And that's closer to the side length I actually want, right? So that tells me that side length y. If I want the whole height of the classroom, what do? Add them together. And let's see, I think I can add those two together. 7 plus 8 is 15. So I think this is reporting an answer of 154 inches. And I don't know, if I'm about 6 foot or 72 inches, does that seem not unreasonable? Classroom's a little bit more than double my height. Okay. Cool. How'd that procedure feel? That seemed, so let's think about what things were important here. It was important, I guess, that I was standing at the same height as that bottom point. Otherwise, that horizontal wouldn't actually be horizontal, would it? So that's something that you needed to have this approach walk. But as long as you can arrange that that's close enough, then you can use this to measure heights of things. And I don't know, like there are lots of things whose heights you might want to measure on campus, like, I don't know, buildings or trees or stuff. Extra credit, come up to my office, borrow from me the avenue level, go measure something. With the added thing that, right, so you'll need that tape measure to make like an eye level measurement. That's fine. You borrow from me a tape measure as well. The main thing I want to see is you doing some trigonometry. I don't know the heights of any of these buildings, so I don't know any objective right answers. Anyone think they might do that? Yeah, cool. Ideally not on a day like today, it's kind of unpleasant out. Pick a day when the weather's kind of nice out, maybe go out with a group of people, take some measurements, do some trigonometry. Nice. All right, so there's the heavily applied portion of today done. Oh, and I guess you don't even need to use that, like, cell phones have like internal angle measures in them, don't they? Yeah, so you don't even need to borrow from me that doodad. You have your own doodads that do something like that.
It says about 11 feet.
All right, what's 11 feet in inches? Is that reasonably close to what we got? Yeah, kind of. Yeah. And how much do you trust the cell phone measurement as well?
Yeah.
That's measuring the distance from you, right?
That is actually.
So that's a totally different number. You measured like a hypotenuse from where you're standing
Yeah, I guess
up.
you're right.
Cool. All right. So that completes the heavily applied portion of today. I want to use this logic to fill in these numbers in quadrant 1 of the unit circle. I'm going to use the information going the other way. So I just trusted that the Google calculator or your calculators can compute trig functions on their own. I didn't worry about how it did it. The next thing I want to do is I want to rigorously determine what trig functions are at pi over 6 and pi over 3 radians, and also pi over 4, because we didn't really justify why that should be root 2. So let's try to do that. So right now we already know some trig functions. What's the cosine of 0? Follow your unit circle if you need. Yeah, but say it louder. 1. Sine of 0?
0.
And tangent.
0 over 1.
0 over 1, also known as 0. We also know at pi over 2, what's the cosine of pi over 2?
0.
Sine?
1.
Tangent?
1 over 0, which is invalid here.
Yeah. Any one of those, right? As long as you don't say that 1 over 0 is equal to 0 or something dumb like that. Then 1 over 0 is undefined, is fine. And we also, let's write down the things at pi over 4, even though we haven't really justified it. What's the cosine of pi over 4?
Right 2 over 2.
Sine?
Right 2 over 2.
Tangent.
1.
Cool. The first thing I want to do is I want to justify this by using right triangles. And here's how I'm going to do it. I am going to construct abstractly a right triangle with the following properties. It's going to be a right triangle, so that needs to be a right angle. I'm going to arrange that this angle is pi over 4 radians. This is a right angle, so that's why there's a pi over 2 there. Pi over 2 is a right angle. Let's just try to figure things out about this triangle. Right, I know the hypotenuse. The hypotenuse is length 1. If I could figure out the adjacent side length, then that would tell me what cosine is. So let's just try to figure out things about this triangle. And I guess let's start with this angle alpha. What do the angles inside a triangle always have to add up to?
180.
Degrees. Everything here is in radians, so let's convert that to radians. How many radians is 180 degrees? You can look at your unit circle, it has that conversion built in.
Pi over 1. Or
It's pi.
pi.
180 degrees is pi radians, because they're both half of a revolution. Oh, cool. So this angle plus that angle plus alpha has to add up to pi. So could you use that to solve for alpha? Let's write down an equation. So the angles have to add up to pi radians. Let's use that to find alpha. So down here I see a pi over 4 plus a pi over 2 from that right angle plus alpha equals pi. Do I look like you could solve that for alpha? What do you get?
Pi over 4.
I hear a pi over 4. Do I hear a second? Do I hear agreement or disagreement with the conclusion that alpha is equal to pi over 4? Agreement? Disagreement? A request that I do some algebra. All right, let's do some algebra. So maybe I'll even ask you. So you solved that for alpha. What did you do to solve that for alpha?
I converted it to degrees. The radians to degrees.
Sure, you could do that. It's not hurting anything, but let's do it directly. Let's do it, because this is just an equation with numbers in it. So I'm just gonna do that. It'll be the same walk you did. In fact, arguably the numbers will be less unpleasant. I just need to subtract those to the other side. Because you did the same thing, but you subtracted 45 degrees and then 90 degrees over.
Right.
So alpha is pi minus pi over 4 minus pi over 2. And let's see, I see a bunch of subtracted fractions. So I guess if you wanted to do it very algorithmically, you need to get a common denominator. What's the common denominator between the lot of them? 4. So this is 4 pi over 4 minus pi over 4 minus 2 pi over 4. And what do you get in that numerator when you do that subtraction?
Pi.
Just pi. Nice. So alpha winds up being pi over 4. All right, people feel okay at that step? And a lot of these like mess around with the triangle games, just start finding things about the triangle until you find enough. And right now, here's where I'll notice those two angles are equal to each other. They're the same size. So the topmost and bottommost right angle, bottommost and bottom right angles are the same. Those two angles are the same. So this is an isosceles triangle. Whenever you see two angles being equal at the triangle is isosceles, the side lengths opposite those two angles will be equal. So that tells me that the side length called A is equal to the side length called B. So far, so good?
Wait, what's B? What side are we at? B's, so that would be,
So those two side lengths are equal to each other. Now let's use the Pythagorean identity. What does the Pythagorean theorem tell me about this right triangle now?
what the hypothesis?
Yeah. So the hypotenuse, which is 1, is equal to adjacent side length squared plus opposite side length, but B is equal to A. That look like you could solve it for A? Solve that for A. It's a side length, so it has to be positive, so you don't need to worry about that plus or minus that appears. So you solve that for A, what do you get?
Y equals 2A squared.
Cool. Now keep going. I want to know what A is. So what would you want to do if you wanted to solve that for A?
Divide by 2 squared. Yeah.
Divide by 2 and take a square root. So 1/2 equals A squared. It looks like A is now the square root of 1/2. And I didn't need to worry about the plus or minus because it's a side lengths are positive. Is that like a thing that should be simplified? I see a fraction under a square root. So I should rewrite that as the square root of 1, which is 1, divided by the square root of 2. What do I need to do to simplify that?
Get rid of the square root under the denominator.
Yeah, I don't like that there's a square root of 2 in the denominator. How do you get rid of that?
Multiply by the square root of 2 to top and bottom.
Nice. And you can always multiply a fraction by 1. Multiplying by 1 doesn't change a fraction. If you multiply by the right kind of 1, then you can simplify something. So you multiply by root 2 and divide by root 2. And what does that become?
Root 2 over root 2.
Nice. So it looks like A is equal to the square root of 2 over 2. This picture is now messy. So I think I'm going to redraw it here. Yeah, this will be fine. So hypotenuse was length 1. This angle was pi over 4. This is a right angle. This angle is pi over 4. The side length A is root 2 over 2. The side length b is also 2 over 2 because a equals b. Let's do some trigonometry now. So the cosine of pi over 4 is adjacent over hypotenuse. Oh, there's no side length called c. So the cosine is a over the hypotenuse, so a over 1. So what's the cosine of pi over 4, according to this analysis?
Did we want also?
Well, a isn't 1. It's just whatever a is, right?
So, 2 squared, or squared at 2 over 2.
Oh, cool. That agrees with what we already said last time, but now you know why it's true. It's true because you can draw a 45, 45, 90 triangle. How about sine?
It would just be 1 right?
Let's see. The hypotenuse is length 1, so that c should be a 1. So that looks like it's just the side length b. So also root 2 over 2, because b is root 2 over 2. That agrees with what we already knew. And how about tangent? B and a are equal to each other?
Yeah.
So this will be root 2 over 2 divided by root 2 over 2. Yeah, that's 1. Groovy. That feel pretty okay? Nice. In fact, I think you could have figured out tangent before you even figured out what a and b are. As soon as you know that a and b are equal, then you could have just said, well, tangent is opposite over hypotenuse, opposite over adjacent, so that'll be 1. All right, so the remaining 2 columns, I'll do the exact same walk. I'll draw a right triangle, that'll tell me something about pi over 6. It turns out that same triangle will tell me something about pi over 3. I'll study that triangle and we'll get some results out of it. So, doing that. So here is where we will begin. Let's start by studying this shaded in green triangle on top. Let's arrange that the hypotenuse has length 1. That's called the adjacent side A, the opposite side B. Let's arrange so that this angle is pi over 6. This is a right angle, so that's an angle of pi over 2. And let's start by doing the exact same thing as we did last time. Let's find that missing angle alpha. Yeah, we've got enough time to do it this way. So, find that angle. If you want to watch degrees, you can, but it won't be theoretically any easier. And once you have the value for alpha pinned down, and maybe you've compared it with someone around you and you're feeling confident, we'll come together.
Yeah, I would agree. Because you do pi minus pi 6 and minus pi 2. And then they all have the same, or they all just
Yeah, so I hold a pi over 3, and the justification is that if you add these 3 angles up, pi over 6 plus pi over 2 plus the unknown angle alpha, they have to add up to pi.
Yeah.
Apparently you solve that, you get pi over 3. People agree with that result? Call for me to do the algebra? All right, let's do the algebra. So I just want to get that angle alpha on its own. And last time I subtracted everything over to the other side, then I got a common denominator. I don't know. Just in order to demonstrate you can do things in different orders. Let's start by adding those 2 things together, and then I'll subtract that result to the other side. So how do you compute pi over 6 plus pi over 2? I guess you need a common denominator. What's 6 is the common denominator? So let's rewrite that as over 6. So 1 pi over 6. Pi over 2 is 3 pi over 6's. So that's 4 pi over 6. And what is 4 pi over 6? Anything simplify there?
2 pi over 3.
Yeah. 4 is even, 6 is even, so you can cancel a factor of 2. 2 pi over 3 plus alpha equals pi. All right. Now there's just a single number added to alpha and the result's pi. So just subtract that to the other side.
Yeah.
Feel good? So alpha is pi minus 2 pi over 3. Play the same game, get a common denominator. Pi is the same as 3 pi over 3. So if you have 3 pi over 3's and you take away 2 pi over 3's, how many pi over 3's are you left with? Just 1. So alpha is pi over 3. Was that helpful, I hope? Excellent. Yeah. So the only thing that made this difficult is there's a pi sitting there and there are some fractions. But otherwise, it's straightforward algebra, I hope. All right. So that tells you what this angle alpha is. It is pi over 3. And now, this triangle underneath is the exact same triangle as above, but just reflected over the line AC. So that means this angle is also pi over 3. That angle is also pi over 6. So as a consequence, tell me what that big blue angle is that I just drew.
2 pi over 6.
2 pi over 6, which simplifies to
Pi over 3. Right.
6 is even, 2 is even, so you can cancel a 2. So now look at that big triangle, the triangle with vertices A, B, and D. How do the angles in that triangle compare?
They're all the same.
There.
A, B.
Yeah, so the angle at A is pi over 3. The angle at B is pi over 3. The angle at C is pi over 3.
The angle at C.
Angle at D.
Oh,
Sorry, no, I think I said wrong. Those 3 angles.
yeah.
Aha, so this is an equilateral triangle then. All of the angles are the same as each other, so all of the side lengths should be the same as each other. This is a very symmetric triangle. So let's write down some equations we get. All of the side lengths of the big triangle are the same. So let's write down what things are equal. So this is equilateral. So what equations can we get out of that? I guess let's list them one at a time. So there's one of the side lengths of the big triangle. There's another one of the side lengths of this big triangle. 1 equals 1 is not exciting. What about this side length? How long is that side length? Also has to be 1, but I already have a name for it. It's 2b. It's made up of a side length of length b and another side length of length b.
Yeah.
Oh, cool. So what's b? Nice. I'm now going to just redraw the green triangle on top because that picture is getting messy. So here's what I have right now. You have a right triangle here. This angle is pi over 6. This angle is pi over 3. That side length is 1/2. The hypotenuse has length 1. I want to know some trig functions. That side length I don't know yet. That side length is length A. I'd like to know trig functions. What seems like the next thing to do?
Um, so, yeah.
Let's find the side length A. Or I guess we already know the opposite and the hypotenuse, so we could figure out sine of pi over 6 immediately. So sine of pi over 6 will be opposite, which is 1/2, divided by hypotenuse, 1. Oh, all of those fractions are mislabeled. Ignore those. So the sine of pi over 6 is 1/2. If I want to know cosine or tangent, looks like I need the side length A, so let's find the side length A. And to do that, let's use the Pythagorean formula, which tells me that 1 squared is equal to 1/2 quantity squared plus A squared. And let's see, I'm a little bit low on time, so let's go through the walk of solving that for A. So I guess to do that, I guess we need to simplify and like subtract something to the other side. What's 1 squared?
1.
What's 1/2 squared? 1/4. So I need to subtract that quarter to the other side, giving me 3/4 is equal to A squared. People happy with that step? All right, now I need to take the square root of both sides. A is a side length. Well, you know what, I'll put the plus or minus there for now. But A is a side length, so I don't need to worry about the plus or minus sign. I know it'll be positive. Do you see any perfect squares underneath that square root? 4. So I can pull the 4 out of the square root, leaving me with just the 3 in the square root. All right, so that side length A is the square root of 3 divided by 2. Is that everything I need to do right triangle trigonometry now?
Yeah.
Cool. And we already computed sine of pi over 6. What is the cosine of pi over 6?
Which would be the root 3 over 2 over 1. Yeah. So
Yeah.
root 3 over 2.
So it is adjacent over hypotenuse, also known as just root 3 over 2. How about tangent?
Sine over cosine, so 1/2 over root 3 over 2.
Cool. It'll be opposite over adjacent. You said sine over cosine, which is the same. That look like something that should probably be simplified?
Yeah.
How does it simplify?
Tell me what the denominator is, I kind of forget it. Over 2, I don't know.
Yeah, the over 2's will cancel, but since you said that with a big old question mark at the end, let's just see that that happens.
It's right there. I got it.
I agree. So I see a fraction in the denominator, so that means I multiply by the reciprocal. So I multiply by 2 divided by the square root of 3. Those 2's cancel. That's why the 2's you wanted to cancel. So whenever you divide both the numerator and denominator by 2, you can cancel those. If you don't notice that, if you follow the algorithm that is how you divide by a fraction, you'll see that. All right, so I have 1 over root 3. I know how to simplify that. I'll multiply and divide by the square root of 3. All right, that doesn't change what the fraction is. I now see root 3 over 3. Yeah. So we had 1 over root 3. But I see a root 3 in the denominator. I don't like that.
Yeah.
So to simplify, multiply and divide by root 3.
Yeah.
The numerator is now just the square root of 3.
Is root 3 times root 3 just 3?
Yeah, because the square root of 3 squared, square roots undo squares. That's why you multiply and divide by, the thing in the square root. Like, it makes the square root go away. Cool, let's put that down. So I know what these numbers are now. The x coordinate is cosine is root 3 over 2. y coordinate is 1 over 2. The tangent is root 3 over 3. And I'm low on time, but let's notice this. Does pi over 3 also show up in this triangle? Yeah, so I can use right triangle trigonometry using that. Sine will be opposite over hypotenuse. What's the side opposite that purple angle? A. So root 3 over 2. What's the hypotenuse?
1.
Nice. So the sine of pi over 3, I'm going to put that in the unit circle, is root 3 over 2. Do you think you can figure out cosine and tangent now? Yeah, probably. Nice. I won't, but that's just because I'm already over time. So here's what I'll ask you to do in advance of the next lecture. Finish up those lines. Check your result by using a machine. Figure out what these trig functions should be. Have your calculator also compute these trig functions, see if it agrees. And if you want to ask questions about it, then ask questions about it at the start of the lecture tomorrow. Stop recording.